So you've done your experiment, gathered all of your materials, you've followed the method, you've got your results. What do we do with it? The results are going to be the recording of all of the observations and measurements that you took. These are called data, or data, depending on how you pronounce it. I'm a data person, so I call it data. It's important to consider how you represent this though. And generally we want to do this before you start an investigation, because if I just get all this stuff and then I'm like, oh, okay, well, what of that do I actually need? Or you might do the experiment and then realize you didn't record something you needed to. So before you complete the experiment, we need to know what our data is going to look like. What are the things that we're measuring? What other values do we need to know? Your results are a display of the findings for your investigation. This includes a table and a graph where applicable of your data. 99.99% of the time, you're going to have a graph. Almost always. The graph is really, really important. You need to label and number each of those things. So your graph, your table, etc. should have a labeling system on it. And often we'll use this format. So you would start by numbering the first table, table 1, and then you would describe what it is. So we might say table 1, the relationship between the volume of water and the height of plant. This would go below the table. So in just a small font tucked underneath the table, we can see, all right, great, that's what that table is. Same thing for the graph. Often you can call it figure 1 or graph 1, doesn't really matter, but we're going to do the same thing. So your first graph might be called figure 1, and again, it says the relationship between plant height and water volume, whatever, and that's going to go below your graph. So that's the labeling system we use so we can keep track. The reason we do that is because later on in the discussion, it's very easy to go as seen in figure 1, as seen in table 1, versus going as seen in the graph, but often you have more than one graph, so it's not really clear. You don't want to just go graph 1, graph 2. We call it figure 1, figure 2, etc. So how do we represent data? There's actually lots of different ways you can do this. Table is nearly always used. We're going to have a table of our information. You can have lists of data. We can have descriptions of the observations as well to support that. We might include photographs of what the thing looked like, what the results were. If it changed color, you might take photos of all the different colors. There's lots and lots of ways we can do this. We're going to focus on the most common, or really the essential criteria that you have to have when representing data. The first one is a table of findings. So this will be basically a table with all your boxes. The column, row, and axis headings must be labeled. So a really bad example of this is I've labeled it distance height, but I've put units in every single entry. And we never do that. We would put distance with units as its heading, and then I just put the numbers following it. Really, it's just saving you effort. We don't want to write cm for every single one. If the heading tells me all of these numbers are in cm, it's much, much cleaner. So distance, height, both in centimeters, and my numbers follow it. I could flip this. I could make this a vertical column, and I could have distance and height on the top and it running down as columns rather than rows. Doesn't really matter. It really comes down to whatever looks best for your data. To look at some examples of past student work, again, we can clearly see headings across the top. Each has units, kilograms, meters per second, average maximum velocity in meters per second, and they've included how that was calculated, so that's nice. Trials, so they've done multiple trials for the same experiment. We can clearly see here's the values and we know what the units are. See how we've got the table label below? This is what I talked about earlier. So table 1 is the relationship between the mass of the body and maximum velocity reached. Another example, this was a pendulum experiment. So we've got pendulum length in centimeters, time for swings in seconds, the period is in seconds, experimental period is in seconds, trials, data. It's a really nice looking table. I cut off the figure label, but they had one below as well. So some examples of really good data. The main thing is headings and units in the top, never units inside the values. So now we're going to graph the data. So we've got our table, we then want to construct a graph. In the next video, I'll talk about how you make graphs. So if you're not sure how to create a graph, I'll go through it. But there's a few essential requirements of a graph when you make one. Firstly, it needs to have the horizontal and vertical axis, sometimes called X and Y axis. In the mathematical sense, needs to have it. So they need to be clearly there. Those axes need labels with units. Just like our tables needed headings with units, the graph has to have labels and units. So we can see here, we've got temperature in degrees C, we've got time in seconds. So we need those units in the axis labels. The graph should have a main heading at the top. Again, it should be clear enough to tell us what the thing is. In this case, it's the temperature of the liquid versus time. All of the data values should be plotted as small dots, not big squares or giant circles. Make them small because it's easier to read. If it's a really big circle, it's hard to tell where exactly it lies on the line. As a side note, again, nearly always, your graph should be a scatter plot without the connecting line. So the line that you can see in this one is actually the trend line. This is not what the graph has created itself. But when you first start and create your graph, it should just be dots with nothing joining it. Excel can use other graph options where it joins lines to them. That's completely useless. Those lines don't actually tell you anything. All it does is a bit of a connect the dots. That's useless. We also want this trend line. So this blue line that I've got here is actually the trend line that the Excel graphing document has created for me. That's really important. The trend line will try and fit through as many points as possible. A really good trend line will touch most, if not all, of your points. A trend line that's not great might start touching the points, and then there's lots of points up here maybe that don't. That could be because of errors, or it could be because you've used the wrong type of trend line for your data. Lastly, you need to include this. Excel will just do this for you, so you don't have to calculate anything, but it's the equation of the trend line. So I can look at the mathematical representation of that line used and the R-squared value. R-squared value is really, really useful, but often people misunderstand what an R-squared value is. So R-squared value tells you how good does your trend line fit your data. In this case, anything around a 0.9, 0.99 is really, really good. The idea is 1 is perfect. If you have an R-squared value of 1, every single data point that you measured is exactly on that line. So you've created a perfect line, straight line in this example, but that's the point. If your R-squared value is really, really poor, it could be because you've got lots of errors, or it could be because the data just doesn't fit that relationship. For example, here I've used a straight line, but in other experiments, maybe it's curved. A straight line is never going to fit curved data, so I might try and change and use like an exponential or a quadratic equation and see if my R-squared value is better. But the R-squared value doesn't necessarily tell you that there are issues or errors with your experiment. In this case, we can clearly see it's a straight line, but if this point was up here, maybe this point was down here, there's a little bit of bouncing around and my R-squared value wasn't great, that I can use to support my argument that there's probably errors here because it's definitely still a straight line, but it just doesn't perfectly fit. So that's probably errors. But unless you can justify that, the R-squared value is just telling you how good does your line represent that choice. So here's an example of a really good graph. So you can see we've got axis label units, got all my data points. In this case, this student has chosen to put the labels on top of each data point. That's okay. As long as it doesn't congest all of your work, that's completely fine. We've got a heading. Nice clear heading. We've got our equation of a line. So this is another straight line we've used. We've got our R-squared value of 0.9567. So we've got our trend line here. This is that blue dotted line. That's good. We've used a scatter plot to see how there's no connecting lines here, just my trend line. And it came from this table of data. So that's what we started with. They used that to construct this table, this graph.